56 multiple choice test questions, 56 multiple choice questions, and then you have 2 case studies. Those case studies, each multiple choice question is worth 2 points apiece. And unless I change it between now and then, which I'm not expecting to do, the case studies are worth, the first one is 6, 10. The first case study is worth 14 points. And the second case study is worth 8 points. One of your case study comes from chapter 5, and one of your case studies comes from chapter 6. So, if you're willing to answer all those case studies, there's one from each chapter on the test. Okay. Answers are in the back of the book for all the case studies. Basically, that's putting the whole chapter together, okay? A case study is like a level 3 test question. It's where you have to basically understand what was in that chapter. Okay, so let's start talking about what we covered that should be able to help you on the exam. The reagent strips. You guys remember the bottle of reagent strips? I think I put them all up. Tell me some things about the reagent strips that's important, like so you don't contaminate your strips.
It has to be white. Yeah.
What temperature do we keep them at? Anybody know?
Room temperature.
Reagent strips are kept at room temperature. Okay, what's one of the first things if you're attacking, you go into a lab you've never been in before, and I tell you to go to work in urinalysis, what's one thing you might look at on the bottle instantly before you start using those strips?
Yeah.
Expiration date.
Yeah.
Right? I mean, you might be using a bottle like in our lab that expired back in 2004. Okay? So you want to make sure it's in dated. What's another thing about the bottle that you guys can tell me about?
It needs to stay shut and away from light.
Right, keep it where light can't hit it. What's one thing they do to the bottles to make sure light doesn't hit them? They're usually black. Now I know that one, they're white, but in other words, don't leave the cap off the bottle and let light get in, okay? What's another thing that comes in that bottle that's very important?
The
Always
instruction.
says, do not eat.
Oh, it keeps it dry. The silica that
What's that thing called? The desiccant, right?
Yeah.
Even though it's something simple, each one of those bottles, I'm not saying all of our bottles do, but each one of those bottles should have a desiccant in it. That desiccant, what a desiccant is a drying agent. So even if there was somehow a little bit of moisture in the air or something, hopefully that desiccant is going to keep those strips dry. Quality control on those reagent strips. Let's go over, now, I may not be hitting every single thing, but let's talk about the things that your book told you about. When would you run quality control on reagent strips?
Every time you
What?
you get a new one.
Okay, so when you open up a new bottle, okay, whenever you open up a new bottle, there is going to be criteria wherever you work at that you have to do that so often. You have to run quality control on those reagent strips. I will guarantee you it's at least once every 24 hours.
Yeah.
Some places have you do it once a shift. That's 3 times a day. But most places, it's gonna be once every 24 hours. You remember me telling you guys, if you happen to be going to work that morning and you look in your reagent strip bottle and there's only 2 strips left, you might as well open up a new bottle. Because if you use those last 2 strips on your quality control, well now as soon as you have to open up a new bottle, you gotta run QC again. Okay? So remember that about the quality control. What's one thing about urines that I told you guys to make sure that basically can interfere with the microscopic or can interfere with the chemical testing?
Sitting too long.
The what?
Sitting too long.
Okay, but if you ever have to store a urine, you wanna avoid
Refrigerator.
what? Refrigeration, right? Refrigeration is the best preservative, don't get me wrong, because you're not adding a chemical. But if you do have a urine that's been sitting in the refrigerator, you have to let it come to room temperature before you test it. First of all that amorphous, it will screw up the chemical reactions on the strips, and it will also get in the way when you're doing a microscopic, because you saw a picture back there of what amorphous looks like, right? It just looks like a sand that's all in it, and it gets in the way of everything. You can't really see through it to see the important stuff like white cells, red cells, crystals. Okay, I've looked all through this test before class this morning. Just trust me when I tell you, go through each chemical analyte that's tested and learn the principle of the reaction. Now, I don't mean that you have to draw out the reaction, but you remember, like, for example, glucose, it says it's called a double sequential enzymatic reaction. You gotta remember that phrase, okay? pH is a double indicator system. That's the principle of that. There's one called the protein error of indicators for protein, right? Remember those principles for each one, and I told you guys, make sure you know that. There's at least 3 of those on the exam. 3 different questions where I'm just saying, tell me the principle of the reaction, okay? Because that will be on your, there probably will only be 1, but that will be on your registry, so I'm trying to make sure that you get those down now. Okay, let's talk about pH a little bit, that pH pad on the dipstick. You as a tech, even though I know that patients have horrible acid-base disorders and all of that, but if you're working in the laboratory and you're doing your analysis, what do you think is the most important thing that has to do with the pH of the urine? Why should you be paying attention to that as a tech?
To know whether it's acidic or alkaline?
Okay, good, right? That's what the pH does, but what is that progression?
It helps you determine what crystals you're seeing.
Yes,
Yeah.
perfect, Bianca. That tells you what kind of crystals may be present. If you got something in the urine, for example, and it looks like this, okay, and you're not sure what it is, you don't even know if it's trash, okay? I'm just trying to draw something, okay? But you see something like that, and it looks like the real deal, but you're like, I don't know, what is that, you know? If you look at the urine, and let's just say that you suspect that crystal, do you kind of agree that kind of looks like a thorny apple?
Yeah.
Thorny apple, all right? Thorny apple crystals are called ammonium biurate crystals, and those are usually seen in alkaline urine. They're usually found in a specimen that is set out at room temperature for a long time, okay? So I put a question or 2 on the exam because I'm not wanting you to play physician, I'm wanting you to play lab tech and tell me, like, why is pH important to you as the person that's testing the urine? Because it will help you if you're doing a microscopic and you see a crystal and you're like, I don't know what that is, but I know it's a crystal of some sort. Look at the pH. If that pH is acidic, you're probably looking at uric acid. That's the most common acidic crystal that there is, okay? But if you look at that urine and you think it's uric acid, but then you look at the pH and the pH is 5, first of all, you need to recognize that's acidic, okay? And so that would tend you to go uric acid, but if that pH was 8, which is alkaline, that doesn't make sense. There's even a question on your exam where I give you like a scenario like that, like which of the following does not make sense? Like a pH of 5 with triple phosphate crystals. That doesn't make sense, right? That's an acidic urine with triple phosphate crystals. Something's not right there. So you would have to pick that out. What was one thing that I told you guys to remember about, you know, I told you there's all kinds of different makers that make these little reagent strips and stuff, but I told you guys to remember one thing about out of the analytes, there's one that usually you have to wait a longer amount of time to read than any of the other things. Anybody remember what the time is on that?
60 to 120.
2 minutes, usually 2 minutes. The leukocyte pad is usually read last. Although there are some companies that make them where they just have you read every analyte at 60 seconds, okay? But it even says that in this book. You've got a review question at the end of the chapter that says the analyte that should be read last on the dipstick is always going to be leukocytes. And that's usually read at the 2-minute mark. If you're diabetic, what's one thing you wanna watch out for in your urine to detect early kidney damage? Microalbumin, alright? The protein pad on the dipstick, what is it most sensitive to? Like if you dip a urine, I'm not talking about microalbumin, but if you dip a urine and it comes up as 3+ for urine protein, okay? What is the main protein that the dipstick is detecting? Albumin, right? Albumin is the major protein in the blood. It makes up more protein than any of the other proteins. But the dipstick is most sensitive to albumin. There are certain proteins that the dipstick does not detect, like Vince-Jones protein that's found in multiple myeloma patients, okay? So if you were to go, like when we do lab today, if you were to go give a urine sample and you dip your urine and you go, oh man, I got protein in my urine, that protein is albumin, all right? That doesn't mean that you have multiple myeloma or anything like that. It's more sensitive to albumin than any other protein. There's a question concerning ketone bodies. You remember how I told you guys go ahead and learn what the 3 ketone bodies are? Anybody know them?
Acetone, acetoacetic acid,
And the beta
and the
hydroxy, blah, blah, blah.
blah. Yeah,
Yeah.
I can't pronounce it.
Acetone and acetic acid, and there's one more.
The beta hydroxy, I don't remember the rest of it, but
Beta hydroxybutyric acid.
Butyric acid, yeah.
Beta hydroxybutyric acid. Which one of those ketone bodies does the reagent strip react with?
Acetoacetic acid.
Acetoacetic acid.
yeah.
If you put the dipstick down in a urine and you see little polka dots on the blood pad, what was that indicating? Good, intact red blood cells. What if you just see a color change like to blue-green, but it's like a broad color, no polka dots? Hemoglobinuria means you've got hemoglobin. So there is, again, I know I've said this, and I'm sure you guys have already got it, but there is the possibility that you can have a 4+ blood in the urine, but not see any red blood cells on the microscopic. Okay? That doesn't really happen that often. Usually you'll know it because your blood will test positive, but you won't see a little red button at the bottom when you spit out the urine. Okay, there's a question on the exam to where, again, there's certain multiple choice questions that you can do that are level 3 questions where you really have to think about it, but there's gonna be scenarios where you have the dipstick results and you have to kind of predict what's causing the patient to be sick. Like if I gave you results and I said, okay, you're looking and all the results come back normal, what they're supposed to be, but the glucose is 4+. If I just told you to diagnose that patient, what would you say they had? The only thing that's in the urine is glucose, blood sugar.
So it's just diabetes.
Diabetes, right? They probably got diabetes mellitus. Now, there's exceptions.
What I'm trying to do right now.
Okay,
That's
alright.
I'm falling asleep.
But if you have glucose in the urine, that can indicate diabetes. What if your lab results showed a positive leukocytes and positive nitrite?
Then I got UTI, probably.
Urinary tract infection, right?
Yep.
What if it showed a positive nitrite, but there was no white blood cells in it?
Okay, they probably lice already, right?
Probably what?
Lice, do they lice, is that what they do? Or they?
Yeah, they can. White blood cells can lyse. But if you ever have a specimen that all it has is bacteria in it, nothing else, there's no white cells, you open it up, it smells like ammonia.
It's sat out too long.
It's probably a
sat out
specimen,
too long.
that just, for whatever reason, it's been sitting without, it's been sitting out at room temperature for over 2 hours, and so your bacteria rapidly multiply.
So since the bacteria wants to keeps growing, all the other stuff just sort of gets eliminated, right?
Well, what happens is when bacteria rapidly multiply and urine sits at room temperature, the pH goes way through the roof.
Okay.
Once the pH gets to 8, any red cells and white cells, they start busting. Okay? And alkaline urine causes those cellular elements to start busting open. Again, that's how come, in my opinion, you do urines as you get them. Don't let a urine sit. You're working in a lab, the golden rule is just don't let urine sit, because first of all, things will start lysing. The other things is those specimens start smelling. So do them as you get them, if you can. Okay, let's talk about centrifuging a urine specimen. What is different from centrifuging a urine specimen from a blood specimen? What's one thing you want to watch out for?
Making air.
You centrifuge it at a lower speed.
Oh yeah, because it can ruin
Because those
everything.
things that can be in urine are more fragile than what's in blood. So your book is gonna tell you the speed of a centrifuge should be 400 RCF, relative centrifugal force, okay? So make sure you read over that section in your book about the speed and the time of a
Yeah,
centrifuge.
because it would make it take longer.
Yep, you spin it slower. So if we're looking at stuff underneath the microscope, we're looking at things underneath the microscope, and you remember I told you about there's a book answer and then there's a tech answer to how many fields you look at?
Yeah.
What's the book answer?
10 fields.
You have to look at a minimum of 10 fields before you start taking your average, right? Okay, so Tanner's looking at a urine sediment underneath the microscope. The urine was yellow and clear, okay? He spun it in a centrifuge, and he noticed there wasn't hardly a cell button at all, but for whatever reason, he still had to do a microscopic on this, okay? Let's say it's a child. Let's say it's a 3-year-old, and your lab rule says no matter what, you have to do a microscopic on anyone that's less than 10 years old, okay? So Tanner knows that he dipped the urine and it was yellow and clear. All the results were normal, negative for everything and falling in the normal range. But Tanner is having to report out a microscopic. So he's looking in there and he can't see anything. I mean, it's like he doesn't even know if he's in focus because there's no stuff in it, okay? What is something Tanner could focus on to let him know that he's in focus?
No, it's slip.
The what?
The slip.
The edge of the cover slip. That's how I told you I do it.
Oh,
But the
as
book tells you to focus on
epithelial.
something else.
It's one of the cells. Yeah.
Focus on an epithelial cell. Why is an epithelial cell something you should initially focus on?
Because it's so
They're
huge.
big and very distinctive.
What's the only thing larger than an epithelial cell?
It's a cast, right?
Right, but not everybody's gonna have casts,
Yeah.
right? So most people, if you look long enough, you can find an epithelial cell in their sediment, even a urine that's completely normal, okay? So remember that, focus on the epithelial cell, or this probably won't be the answer on your registry, focus on the edge of the cover slip too. You can do that. You remember those COVA slides I showed you? I gave you guys a long lecture over something about the way I used to do urines, where you just take a drop of urine sediment, put it on a microscope slide, put a cover slip on it, and look at the stuff underneath the scope, right? And I told you since then, they don't really like that way because techs do things different. Aunt may put a big drop on the microscope slide every time, and I may put a real tiny one, okay? Aunt may have her cover slips that almost cover the entire slide, and I may like the little square ones, okay? So they developed these things called COVA slides, where each individual well is the same exact volume. It has the same amount of room in it, okay? And they developed ways to where they tell you, for example, you have to start with 12 mils of urine to spin it in the centrifuge, okay? Why am I telling you guys all that stuff? If you do everything the same exact way on every single patient, what is that helping you with?
Accuracy.
It's standardization. You're standardizing it. You're making it in a way that every patient is treated the same, okay? So, now listen up right here, okay, because I'm leading into another question. So if I take 2 conical tubes of Haley's urine, okay, Both of them have Haley's urine in it, and I start with 12 mils on this one and 6 mils on this one, okay? Let's just go through everything, and let's just say that I get down to the point where I spun both of these down, and I've got sediment in each one, okay? What's wrong with that? Why is there a discrepancy in that?
Because it's
Volume.
different. There's more in that one, so you're gonna have more sediment that falls to the bottom than the one that has less, because obviously there's not as much urine in it.
Because let's just say that I am the type of person that I want to only have 1 mil of urine, and then the sediment, you agree that you're gonna see less cells in this one, right? Because you started with 6 mils in this one, and you started with 12 mils in this one, so you're actually going to see more cells in this tube than you would this one, but it's the same urine.
You can get a better idea because you have more substance to work with.
Yes. So you need to do it in a way where it's standardized. Every lab's gonna be different. You may work at a lab that says, look, just every single one start with 6 mils, or but try to do them all the same. It is not a perfect world. You will not be able to do that every time, especially when somebody sends you a urine that has 1 drop. I've seen that happen. I've had a urine specimen sent to me before on a child that they were having a hard time getting any urine, and there was 1 drop of urine. What would you do in that situation?
Call them and ask which test they want done.
Yes, I think I've told you all that already.
Yeah.
Yes.
So, I probably say the same exact lecture every time, but anyway, good information, let's see. What in a urine sediment do you need to worry about swimming or motility?
Pseudomonas.
Trichomonas, you got darting motility, okay, you can see in trichomonas. What's something else that you may worry about swimming? This is kind of a trick question,
Well,
but.
sperm don't swim because
Well,
you're.
urine is, sperm is toxic. Urine is toxic to sperm.
So I just want you to remember, you will see spermatozoa in urine, but it will usually be dead still, so you kinda gotta pay attention, like on that codichrome back there, look for that little tail, okay? Usually where you'll see 1 sperm, you'll see more, but they're all gonna be dead. But the only other thing that has motility is gonna be trichomonas. Now, there is something that will kind of shimmer and shake, and what's
Oh,
that?
the white blood cells. Wait, no.
Brownie and
Well,
blue.
you're talking
Yeah.
about a glitter cell, but
Yeah.
don't think that too far into it. Bacteria.
Yeah.
Bacteria will be mobile. It'll be moving a little bit. Sometimes it's really moving, and sometimes it just shakes in one place. This is not on your test, but I'm just telling you, when you become a tech, always remember the minute that you get your, you're gonna get real fast, guys. I know right now you may not think that, but just trust me, you're gonna get real fast where you put a drop on a slide, put it in a microscope, and it's in focus. You're gonna get so fast that you have it in focus before the fluid has settled underneath the cover slip. So don't mistake that for movement. Like if you see a white cell just kind of going like this across, but you don't see a flagella or a tail or anything, that's not trichomonas. That's just that you got it in focus so fast that the fluid is not settled underneath the cover slip yet. What's the worst thing you can see out of all the sediment we've talked about? What do you think the worst, absolutely worst thing as far as diagnostic that you can see out of all the urinary sediment? Nope. Nope.
It's on the cast.
Nope. Actually, one of the epithelial cells.
Not trans.
A renal
Yeah.
tubular epithelial
The
cell.
one you pointed out.
Remember I told you, I said they're rare, but they can indicate end-stage renal disease because you're actually like seeing things starting to come off the tubule itself. That's where those renal tubular cells are at, or on the they're in the tubules, all right? So if you start having tubular necrosis or something like that, you can actually start seeing those renal tubular cells, all right? That's probably one of the worst things. Now, there is something. If you see mononuclear cells, remember what I told you, there's one thing that you can see. If you start seeing cells in a urine sediment that, like, here's a red cell, here's a white cell, you see little granular contents in it. But if you start seeing cells that look like this, what would you think about that? And I'm not talking about a transitional epi. That's considered a mononuclear cell, and you would maybe refer that to cytology, to a pathologist. This could be a malignant cell that has found its way into the urine. So if you ever see a cell, I can't describe them because they're all gonna be different, but if you're ever looking at your, in all your analysis departments, they're gonna have a chart, like I told you guys you could look at, where you can look at things for reference, like what is that? But if you see something that just looks like that, and it's unlike anything you've seen before, you're like, that's a cell, but it doesn't look good. It's not a white, and it's not a red, it's not a squamous. You want to refer this to cytology or histology, because this could be a malignant cell that's found its way in the urinary tract. Okay? That's in your book too. Where are casts formed in the nephron?
Proximal.
Proximal.
Distal convoluted tubule.
Yeah, right there, like where it curves going into the collecting duct. You remember you got the glomerulus, proximal, and distal convoluted tubule, right where Darren is saying, like right where the curve is, and the distal convoluted tubule going into the collecting duct. That's what really, that's the shape of the cast that you're seeing. A lot of times is actually the shape of that particular distal convoluted curvature right there. Okay, that's why the casts are big, they break off. What's the worst kind of cast you can see?
The waxy.
Yeah, you want to stay away from those waxy or broad casts.
Are they not all made out of modulin?
Uromodulin. You guys want to write that down. Casts are made out of a substance called uromodulin. That's what the protein is made out of, uromodulin. I've still got about half this exam to go, so let's take a break, 10 minutes. So, getting back to the microscopic, just as far as test questions that can be asked about it, what is something that you might confuse mucus with?
Confused what?
Oh, maybe the ghee?
Highland.
Oh,
Yeah.
Highland cast.
Amorphous?
Highland cast. Remember I told you guys, if you ever feel like you see a Highland cast means you got first of all, you've got the microscope in real good focus. The Highland cast is just a faint line, trying to draw it faint. It's just a faint line like that, okay? That's a Highland cast. But sometimes you'll see like just little, it looks like little hairs or something in there, but that's kind of mucus. Okay, for whatever reason, books like to tell you like, what can you mistakenly call mucus, or what can you mistakenly call a Highland cast? They interchange with one another. Okay, so just remember that. Now I think that there's a Kodachrome, and I think I told you guys I didn't like it, but it's got a picture of mucus and it looks like that. You know what I mean? And they're calling that mucus. But for the most part, sometimes you'll look at a urine sediment and you'll see something that looks like that all in the background, and that's mucus.
Mm-hmm.
Doesn't mean your patient's sick or anything. But sometimes you'll see,
Looks like a parasite.
like Darren had said earlier, casts are usually made up of a protein called uromodulin. Remember
That's
that.
actually on the page 153, the technical tip.
Yeah. Now, I think Jason kind of told you guys one time
153.
that it used to be called a protein that was called tam horsefall. So if you happen to read over that in your book, don't put that as the answer. The answer is uromodulin. All right. You're going to have to be able to recognize or distinguish crystals, categorize them. Kind of think of them as there's acidic crystals, there's alkaline crystals. Most all crystals, believe it or not, are considered non-pathologic. Crystals can appear in the urine just because they set out at room temperature for a long time. But there are certain pathologic crystals, and you need to be aware of what those are, okay? Like the ones that just come to my mind right off the bat, leucine and tyrosine. Those are two crystals that you will see in people that have liver problems, all right? Leucine and tyrosine. They are still very rare. You very rarely see leucine and tyrosine, but those are considered pathologic crystals. There's another one, cysteine, all right? Remember six-sided cysteine. Cholesterol crystals are supposed to be abnormal as well. So categorized crystals, there is a good section in your book, I was looking at it earlier before class on your review questions, where it's got matching, for example, and it tells you the crystal, and then all it does is give like descriptions for crystals, like six-sided, coffin lid, envelope shaped appearing, thorny apple, okay? That is a great study guide. I mean, just knowing those matching right there will probably get you a couple of questions on the test right. In other words, descriptions for a crystal. On your registry, they may have a perfect picture of it, but they may also describe it. And if they describe it, you've got to be able to figure out an answer for that. Red blood cells can come in 3 different shapes, right? Three different categories. You got a crenated cell. Why would you see crenated red blood cells?
Acidic urine.
Nope. Concentrated. A urine that is very concentrated, in other words, it's got a real high specific gravity. There's a word for that, it's called hyperthernuria. Hyperthernuria, okay? That is a real concentrated urine, can cause red cells to be crenated, like so. Okay, that's a crenated red cell. If you see a red cell that appears kind of just, where you're seeing only the remnants of the outer membrane, that's called a ghost cell, okay? You're gonna see a ghost cell in a urine that is hypotonic or hypothenuric. A lot of water, they start to swell, right? If you're in blood bank and you're making a red cell suspension and you happen to squirt water in there instead of saline, the first thing that's gonna happen is you're gonna see that fluid just all of a sudden, boom, it kind of goes pink. And it's because all your red cells just busted, okay? So if a red cell stays in a hypotonic urine long enough, say a urine that has a specific gravity of 1.004, okay? That means there's a lot of water in it. That urine, eventually that red cell is going to bust and you're no longer gonna see it. And then you've also got what's called a regular red cell, okay? So, crenated cell, ghost cell, whatever, regular cell. Usually ghost cells will be a little bit larger than normal too because they're swelling. Okay, what's that substance that'll be in the urine if you take it straight out of the refrigerator?
Amorphous.
Any questions? All right, I wanted to, if you guys want to, let's review some more urine sediment back here, some pictures, and then I'll go through this quick.